And welcome back to question 9. Now, question 9 is very long. There's a lot of stuff in it. So we're looking for acid, base, neutral, strong, weak, completely, partially, not dissociated. If it's an acid or base, what definition makes it an acid or base? What ions exist in solution at equilibrium? H plus, OH minus, POH, concentration of all ions in solution using the exam resources. Right. Okay, that's a lot of stuff. Let's start at the beginning. So the first one that we get asked about is HI. HI. Okay, and the first thing that we want to know is that an acid, base, or neutral? Well, okay, first thing I'm actually going to see that if I can find is this in my list of strong acids? Because that's the easier thing to check. So strong acids, strong bases, HI is a strong acid. So since it's a strong acid, that means that it's an acid. It is strong, both in terms of being a strong acid and a strong electrolyte. Meaning, since it's a strong acid, it completely dissociates. All of those ions then conduct electricity, which make it an electrolyte. It is completely dissociated. All strong acids are completely dissociated, which is why we have no Ka for them. Because they're completely dissociated, if we were to look at the Ka value, since there's no HI left, that concentration on the bottom would be 0. That would be undefined. So it is an undefined thing if we try and look at a Ka for a strong acid. Okay, so sorry, I got lost. So it is completely dissociated. If it's an acid or base, by what definition is an acid or base? Well, okay, so this is HI. HI can act as an acid by donating H+. That means that it's a Lewis acid, or sorry, an Arrhenius acid. It's also a Bronsted-Lowry for the same reason, because it donates H+. The question with Lewis is, would HI be able to take a pair of electrons to be a Lewis acid? And the answer is no, because once I've donated that H+, I'm left with I-, right? And the Lewis dot structure for I- is this guy. And of course, we're supposed to put that in brackets like this to show that the charge is on the whole thing. Oh, good Lord, you can't see what I'm doing. Holy back. Sorry, this is what I'm talking about. So in order for it to be a Lewis acid, it would have to be able to accept a lone pair. It can't do that. So it is not a Lewis acid. All right. What ions exist in solution at equilibrium? Well, there's no HI left. There's H+ and I-. That's what I've got. We want to know the concentration of H+, the concentration of OH-, the pH and the POH. Oh, Lord. Now, did they give me a concentration? No, this time they didn't. So what I'm going to tell you is, whatever that concentration of HI is, that's equal to the concentration of H+, and that's equal to the concentration of I-. By that same idea, if I wanted to look at what's the OH- concentration, that's equal to 1 times 10 to the minus 14th divided by the H+, my pH equals the negative log of whatever my HI concentration was. And once I find my OH concentration, POH equals the negative log of that. Okay. Helpful? Maybe. And of course, I can't solve for actual concentrations because I didn't give you any concentrations to start with. Now, since I know what my intention was, I can tell you what I was hoping that you would do. I was hoping that you would be given an actual concentration and then use that to find the numbers that go with this. You may remember that there was the first test, there was a table like this on that test. If you have an initial concentration, you should be able to solve for those values. So I'm going to give you an example of that so you can see what it would look like. You should be able to do this on your own given a concentration. This is what you would be responsible for telling me on a test if I didn't give you a concentration. Now, let's assume that the concentration for this, we're talking 0.05 molar, and we're going to make that assumption for all of these species. If that's the case, then 0.05 molar is what we have for that, for my H plus and my OH minus. So my pH is the negative log of the 0.05. Which gives me 1.30. I can find my OH minus by taking 1 EE to the negative 14th divided by the 0.05. That gives me 2 times 10 to the negative 13th for that. My POH is going to be the negative log of that. Negative log, second answer, enter. 12.69. And if I take 12.69 and I add 1.30, notice that I get almost 14. And that's because I rounded my 1.3 rather than looking at all of the numbers that I had when I took the negative log. So if I took the negative log of 0.05, if I had used all of these digits plus negative log of 2 e negative 13. If I take those two numbers, that gives me 14, which is exactly what I would expect. So I can find the OH minus either by using KW directly or by using POH plus pH equals 14. Either one works. Doesn't matter how you get there. It just matters that I can get there. Now, if you can't remember how to get there, then that's why we're going to talk about this right here. So I knew what my H plus concentration was because my HI is a strong acid. So my H plus was 0.05. Since I have 0.05, if I want to find my OH minus, I do 1 times 10 to the minus 14th divided by H plus. That gives me my OH minus. I then take the negative log of the OH minus to get the POH. I can take the POH and subtract that from 14 to get the pH. Or I can go for my H plus to start and take the negative log of the, take the negative log of the H plus to give me pH. I can go around this in all kinds of different ways. This is what the fun box is for, is to remind you how you do all of those things. you should be able to calculate all of these values for any acid or base that you are given. And it is important that you're able to do so. Let me give you some examples why that might be important. If you are working with a basic solution somewhere and somebody manages to ingest it, you need to know, and you happen to be a nurse, doctor, whatever, somebody in the emergency room, you need to know what that pH is going to do, right? You need to know what that effect is going to be. And then you need to know how you can counteract that. It may be important that you are working with something, say you're working in an industrial setting, you need something that's acidic, but somebody dumps a bunch of soap on it. Soap is usually made of lye, which is OH minus. So that pH is going to change based on the concentration of the OH minus, if you know it, which you should know from looking at the safety data sheet, but I won't talk about that too much. Then you can find out what effect it should have on your H+. Okay, these things are important. It is necessary in many, many different places to be able to know the relationships there. So that's why we do this. Okay, so that takes me through concentration of all ions in solution. Well, my ions were H+ and I-, so I got them. Yay! So that was HI. Now we're going to go to the next page. And we're going to go line 2. And this is HF. And I know that it might be possible, it might be reasonable to think that we're going to do the exact same thing that we just did. But I can tell you right now that that's not what we should do. And that's because HF does not appear in this list. HF is not a strong acid. It is the only halogen that is not. And that's because it's really, really small. And so it's very difficult for it to come apart. So what we find, if we scroll far enough, or if we turn pages, is that HF is in this list, hydrofluoric acid. My Ka for that is 7.1 times 10 to the minus 4th. Now, again, we're still assuming 0.05 molar. Okay. Now, I'll tell you how this would work if I didn't have that. Now, given that it's in the weak acid list, it is a weak acid. Anything that's not on my strong acid list is a weak acid. So it is an acid, it is weak, it is therefore a weak electrolyte. It is partially ionized. And again, that's because it's a weak acid. It is a base. It's an HF. So it's not a base. It's an acid. Good Lord. And the reason that it's an acid is because it can donate that H+. It can. That means that we fit the Arrhenius description and the Brønsted-Lowry description. If I were to look at the F-, I have this structure right here. This is a full octet, so he does not want to have an additional set of electrons given to him. He actually is not in a place where he can do that either. Since he's in the second row, he has no d orbitals available to him that are empty. He doesn't have them. So that's not something that we can do. So he cannot be a Lewis base. Acid. Crying out loud, I can't remember what I'm talking about. Okay. What ions exist in solution? Well, we know what we had before. We had H+, we had F-, oh, okay, we had I- last time. Now we also have HF. HF is not an ion, so the ions that I have are the H+ and the F-. H plus, OH minus, pH, POH. Okay, fine. So I have a Ka that's equal to 7.1 times 10 to the minus fourth. Using an ice table, I'm going to make it really tiny because we should know what they look like at this point. So this is 0.05 in this case. These are going to be 0 to start with. This is going to be 0.05 minus x. We're going to make the assumption that the x is small comparative to the 0.05. I'm not going to ask you to do the check on that. It is appropriate to do the check on it, but we're not going to ask you to do that. Our H plus and our F minus are both going to be x. And so we know that this is equal to x squared. All right. Now, if I don't know what the HF concentration is, then, oh, actually I can. I don't need to know what the concentration of HF is to tell you what this is going to be, right? Because I can take the square root of 7.1 times 10 to the minus fourth, and that gives me my x. And of course, x is then 0.026. And it's actually only 1 sig fig, so it should be 2.03. That's my H plus. pH is the negative log of that. So that gives me 1.57. If that's my pH, my POH equals 14 minus the 1.57. Which gives me 12.42, actually 12.43. We normally report pH values to 2 sig figs, pH and POH. The only other thing I haven't calculated yet is my OH minus concentration, which is going to be 1 times 10 to the minus 14th divided by the 0.03. Which gives me that happy thing. The other thing I could do, my OH minus equals 10 to the negative POH. So if I take 10x negative, my POH was 12.43-ish. And technically I can still see it. So 4, 2, 5, 6, 2, 9, 1, 7. Now, the reason that I was attempting to do what I was attempting to do is that we should know at this point that we shouldn't be rounding when we're doing additional calculations. It does lead to rounding errors. So 3.75. See, that's not exactly the same as what I had when I did it with the other way. 1 times 10 to the minus 14th divided by the 0.03. And part of that is the difference in the calculations that we get from all of the rounding that we do. How do I know that this is the case? Well, I always do it this way. And I realize that this is probably overkill as far as you guys are concerned, but 7.1 e to the negative 4. I take the square root of that. That gives me that 0.26646, which we rounded to 0.03. I then take 1 e to the negative 14th. And divide it by that, which gives me 3.75. See, that looks more familiar, right? So we see that there's a rounding error there, and it's because of some of the things that we've already done. Given that my pH is this number right here, or my, H plus, and of course, Ka, H plus, that makes this OH minus, based on the math that I've done, this would then be pH. This is OH. I hate it when I can't type. And so if we are to take 14 minus this number right here, helps if you're calculating things, as our alternate way to do this, that gives me 12.4. And notice, they look exactly the same. So this is what I'm talking about when I'm talking about rounding errors. I'm not going to do this for everyone, but that's what we're talking about. So this is why we want to maintain as many of those numbers as we possibly can while we're doing this. Now, I found my OH minus, and I think that yes, 3.75 times 10 to the minus 13th. Okay. Is that everything? Oh, that's almost everything. I also want to know what the concentration of HF that's left is. And of course, the concentration of HF that's left is that 0.05 minus the X, which is the 0.03, which leaves me with 0.02. Now, realistically, I'm going to show you this. I don't expect you to do it, but I'm going to show you this. We can only ignore X if it's less than 5% of the number that we started. So we calculated that our X value is this right here. So we have our initial value, which is 0.05. We're going to take and divide this number by this number, and then make that a percentage. And it's 53%. So that is not a valid assumption to make. The way that we really should be doing this calculation is to say, okay, I have x squared divided by 0.05 times 7.1 e to the negative minus x. And that expression is equal to my 7.10 e to the negative fourth. Since that's the case, when I multiply over, I end up with x having a value of 7.1 times 7.10 times 10 to the minus fourth. I end up with an x squared, and I end up with a 0.05 times that right there. And that's my C value. So I know that there's an A. That A value goes with the x squared, so that's a 1. My B value is the one that we calculated here because that's the one that goes with x. And my C value is this one that's over here, right? Given that that is the case, then I can, and I always have to do it this way because I can't ever remember the damn equation. So my x is going to be equal to negative b, and of course I do it this way, b e squared 4ac, and then 2a. So this is negative of that. This equals that squared equals 4 times a times c, and this is 2 times a. And then I do my happy math. So this is going to be my, the one where I add. And this is going to be the one where I subtract. So this equals my negative b value plus SQRT is the square root of b squared minus 4ac. And of course, this whole thing, the minus b, this whole thing is divided by my 2a. It's easier for me if I just start. Negative b plus SQRT square root of b squared. Oh, wait. Yes, I've stopped talking. Bear with me just a moment. is gonna drive me crazy. I know what it means. Those are all numbers. Anyway, we shouldn't be not making that assumption. I'm just gonna let it go because why should I do this? So I'm just gonna let it go. That is not a good assumption to make in this case, in which case we should be doing it the long way. That is the way that we should be doing it. But I also understand that you guys are not in a class where it really matters that you do that. If you're going to take a bunch of chemistry, you will figure out how to do that and they will make you do it. So we're going to let that go for now. I think that was everything. POH. Yes, I've got all my values for HF. Hooray! I'm going to give myself some space. I keep forgetting that I need to write my dates that way. I've gotten lazy. All right, MgOH2. This is 9. 3. MgOH2. We'll look at our list. Flippy, flippy, flippy. Now, MgOH2 is not listed here. However, we do know from our solubility rules so I don't see it in my strong acids. I don't see it in my strong bases or weak bases. And so I might be like, I don't know what to do here. But what I'm going to tell you is let's go and look at our solubility rules. Except for those in rule 1, carbonates, hydroxides, and oxides are insoluble. Oh, okay. So we're not going to have a ton of it. So this should be a base. It is a weak base. Weak enough so that it doesn't even appear in that list. Okay, so it's a weak base, which makes it a weak electrolyte. Generally speaking, you'll find that if it's a weak whatever, it's also a weak electrolyte. Strong whatever is a strong electrolyte. It is only going to be partially dissolved. It is a base because of the OH minus that it gives up. Since it donates the OH minus, the only thing that fits our Arrhenius definition, which is the donation of the OH minus. When we look at our Bronsted-Lowry, that is the ability to accept a proton, which it can do. When we talk about it being a Lewis acid or a Lewis base, I don't believe it is. Oh, that's right. Backwards. So a Lewis base needs to have a lone pair that it can donate. And of course, OH minus does. So let me draw you a Lewis structure for that. OH. That's my Lewis structure. One of these lone pairs can be used as a base, and therefore it is also a Lewis base. Okay. So notice that I'm checking against each of those things. It's not necessary that you always do that. If you can tell me one of them, it's fine. Like if it's a base and it's a base because of this, then that's okay. But I want you to be aware that you should be able to answer that question for all of those. So, what ions exist in solution at equilibrium? So we're going to end up with some Mg2 plus, some OH minus, and of course, MgOH2, which is really going to stay a solid. But that's what we got. Okay. Now, is it given that it's not really soluble, the question becomes, how do I deal with that? And the way that we're going to look at that, instead of looking at for a KB for that, what I have to look, since it's not soluble, I have to look at the KSPs. But I actually don't have one. So we go straight from lead into, oh, there it is, MgOH2 is magnesium hydroxide. Yay, I found it. So KSP equals 1.2 times 10 to the minus 11th. That's equal to the Mg2 plus times the OH minus squared. And so that ends up being a 4x cubed situation. And if you're unclear on how it's a 4x cubed, then we can talk about that. I then need to use my calculator. And I've got 1.2 E negative 11. I'm going to divide that by 4. And that gives me 3 times 10 to the minus 12 is equal to x cubed. I take the cube root of both sides. And that gives me an x value of 1.44 times 10 to the minus 4th, right? In order to look at what my OH plus minus is, however, that's a 2x. That's how we got there. And so since that's a 2x to get OH minus, then we have to multiply this value by 2 to get the OH minus. And so my OH minus is 2.884499141 times 10 to the minus 4th. Okay, awesome. I can take the negative log of that. Three point 539929568 6. And then I can do 14 minus that value. And then my H plus is equal to 10 to the negative pH. And that gives me 3.46 times 10 to the negative 11. And notice that I did round that one because I'm not doing any calculations with any of the other numbers. That takes me through H plus, OH minus, pH, POH. Concentration of everything else in solution. My MgOH2 is going to be almost exactly what I started with, and it's not going to be dissolved. It's all going to be solid. So we don't consider that. Woohoo! That was fun. So let's talk about NH3. So my NH3 is a base. It is a weak base. And I'm just going to B/E, so weak base / electrolyte, or weak A is going to be acid / electrolyte. Completely, partially, or not dissolved is partially. Dissolved. It is a Lewis base. Okay. So when we talk about bases for the Arrhenius definition, we're talking about OH minus donors. There is no OH minus that we're going to donate in this case. In the So Arrhenius doesn't really count, although the reaction does give us an OH minus, but it doesn't donate it. The Bronsted-Lowry is a proton acceptor, and it is a proton acceptor, so it is also a Bronsted-Lowry, okay, and that's because it accepts the proton. But it is a Lewis base, again, because this is our Lewis structure. And so this lone pair is what we can donate for our Lewis base. So we hit both of those definitions. What ions exist in solution? NH3, NH4 plus, NOH minus. And what are all of our values? Now, if I remember correctly, right here, we calculated all of this stuff, right? So we had expressions that we would be able to use if we had a value. So what I can do, because I can cheat, is I can say, okay, let me take all of this with me. I copy that. And of course, now that I've got this here, I can make some substitutions, right? So I know what my KB is, or at least I should. I can go find it. (1.8 times 10 to the minus 5). And I'm still assuming 0.05 is my concentration. So now I can take and put that 0.05 into this. So I take my 1.8 times 10 to the minus fifth. I multiply that by 0.05. That's equal to x squared. And again, we are making the assumption, and it's not necessarily a good one, but we are making the assumption. So we're going to take our 1.8 second EE negative 5. We're going to multiply that by the 0.05. It gives me 9 times 10 to the minus 7th. And that's equal to x squared. So my x is going to be square root of that. And so I get 9.48 times 10 to the minus 4th. That's equal to my OH minus concentration. It's also equal to my NH4 plus. Okay, so they're both equal to that. If that's my OH minus, I can take the negative log of that. I can take 14 and subtract that. And of course my H plus equals 10 to the negative that value right there. And that's 1.05 times 10 to the minus 11th. And that's everything for that. Sweetness. Sorry, I just thought of something. I did. So, So that's all of the map that we were just doing right there. Okay, so that's for NH3. I'm going to take just a little recording break for just a moment, and I'll be right back. Okay, so that's our NH3. That's going to take us to NaOH, and that's awesome. NaOH. NaOH, just in case you can't remember, is in our list of strong acids, or sorry, strong bases. So it is a strong base. That makes it a strong B/E. So strong base, strong electrolyte. It is completely dissolved. It fits all of our definitions. So Arrhenius, because it donates the OH minus group, Bronsted-Lowry, because it can accept a proton, and the O on the OH can act as a Lewis base by donating a lone pair. So base by Arrhenius, Ronstadt Lowry, and Lewis. Ions that exist. Where'd it go? Oh, and this is actually 9, 5. So all we're going to have is Na plus and the OH minus, and of course there's going to be some H plus, just because that's around all the time. In this case, the OH minus is going to equal the Na plus, which is whatever the NaOH is. And yes, we are going to make our assumption, but I'm going to show you what it looks like before we make our assumption. And so our H plus is going to equal 1 times 10 to the minus 14th over the OH minus. We can take the negative log of H plus to give us pH. And we can take POH equals the negative log of that concentration. So that would give me my H plus, my OH minus, my pH, and my POH. Okay, so again, without any value, that's where we'd end up, but we do have a value. So if we make the assumption that the OH minus equals to 0.05 molar, then that means that our H plus one times 10 to the minus 14th divided by the 0.05 and gives us 2 times 10 to the minus 13th. I'm pretty sure we did this previously when we had I think it was HI that we did, and we should see the same kinds of values. So that's our H plus. We can take our pH equals the negative log of that concentration. Our POH is the negative log of the 0.05. And that's all of our answers. Woohoo, that was fun. It only really takes a long time when it's a week something. All right, our next one, so 9VI, is HNO3. And HNO3 is on that list of strong acids. Sorry, I actually shouldn't do that, but that's all right. I'll move it a sec. So HNO3, nitric acid, is on our list of strong acids. Just as I stated. Cool, awesome. That means that strong acid completely dissociates and of course it's a strong electrolyte. What ions am I going to have? H plus and NO3 minus, and of course there'll be some OH minus as well. If we take a look at that, our HNO3 concentration is going to equal our H plus concentration. It's going to equal our OH minus concentration. No, it's not. Jeez. That's not the one I meant. The NO3 minus. And we will make the assumption that that's 0.05. If we were to look for the OH minus, that's the negative, sorry, it's 1 times 10 to the minus 14th divided by the H plus. And then we can take the negative log of that to give us POH. And then the negative log of that guy is our pH. So, since we have an OH minus, an H plus for this, our OH minus is going to be 1 times 10 to the minus 14th divided by the 0.05, just 2 times 10 to the minus 13th, or then our pH is then going to be the 1.301029996, and our POH is going to be equal to the 12.69897. Okay, so same values, just opposite sides, because, you know, we were talking about base and now we're talking about acid. Whew. Okay, fine. So now let's talk about 9BII. Okay. I scrolled. So acid, base, or neutral for NaCl. NaCl is neutral. It is neither an acid nor a base. It is a strong electrolyte, however. Its concentration for Na plus is going to equal the Cl minus because it is a strong electrolyte. It completely dissociates. And of course, that means that this is 0.05. Okay. In this case, because we're not talking about an acid or base here, our H plus is going to equal our OH minus, which is going to equal 1 times 10 to the minus 7th. Okay, because this is a neutral solution. Okay. Awesome possum. That one was easy. BaCO3. Well, let's talk about this for a second. So when BaCO3 goes into solution, we get a Ba2 plus a CO3 2 minus. And there's something in my head that sticks out about this CO3 2 minus. What that is, I'm not sure, but it's not in this list. And so let me go take a look at this one table that I vaguely remember. Acid-base properties of salts. So one of the things that's on here, no, actually it's not on here, but it should be. Anyway, we can look at our diprotics, and what you see when you look on this table is that carbonic acid H2CO3 is on here. Now, that's not the CO3 2 minus, or is it? The HCO3 can donate its proton to become CO3 2 minus. All words. So CO3 2 minus then has a conjugate base, Kb, of 2.1 times 10 to the minus 4th. So I know I'm going to have Ba2 plus in solution. And I know there's going to be some CO3 2 minus. But what happens is I then have CO3 2 minus plus H2O going to give me HCO3 minus plus OH minus. Okay, that's going to affect the concentration of the H plus and the OH minus in solution. And so we have to take that into account. The way that we do that, we know that the concentration of the BaCO3 was 0.05. When I look at my solubility rules, what it says is, except for those in rule 1, carbonates, hydroxides, oxides, and phosphates are insoluble. Oh, okay. So that means that my BaCO3 is only slightly soluble. Right. So that means that there should be a KSP for this, correct? Oh, and there is. KSP Ba2 plus. So this isn't 0.05 times the CO3 2 minus. And that equals 8.1 times 10 to the minus 9th. Okay. So 1 to 1, this is then an x squared. I take the square root of that. I take the square root of the 8.1 times 10 to the minus 9th. And that gives me my Ba and my CO3 2. Minimize this so I can look at a calculator. So I need a square root of 8.1 second EE negative 11. Nope, not negative 11. Negative 9. It gives me 9.5 times 10 to the minus 5th. So my Ba 2 plus equals my CO3 2 minus, and that is 9 times 10 to the minus 5th. That I can then put into this. And so when I'm looking at my ice table, for CO3 2 minus plus H2O going to HCO3 minus plus OH minus. My CO3 2 minus is 9 times 10 to the minus 5th. We ignore this. We say this is, both of those are 0. This is 9 times 10 to the minus 5th minus x. This is x. This is x. So I end up with the value for that, 2.1 times 10 to the minus 4th equal to x squared over 9 times 10 to the minus 5th minus x. And if I set up all of my happy math, I end up with x squared minus 9 times 10 to the minus 5th x. Ooh, sorry, wrong one. See, this is what happens when I do too many things. 2.14 times the minus x. So when I move that over to the other side. So I multiply it over here, it's still negative. I take it over there, it's positive. 2.1 times 10 to the minus 4th x plus 2.1 and it gives me 1.89 times 10 to the minus 5th. And then, of course, I can set this as my A, my B, and my C. And I can't do that on this calculator, so let me pull up this again. You've lost your mind, Cat. So painful, isn't it? Don't worry if you don't understand all the Excel crap. It's not important. Okay, so this is my positive value right here. Whew, that's my X. So now if I want to look at 3.25 times 10 to the minus fourth, 3.25 times 10 to the minus fourth, and of course we can take 9e negative fifth minus and gives me 5.75 times 10 to the minus fifth. Whew. So that gives me my OH minus. That gives me the concentration of my Ba2 plus and my CO3 minus. Awesome possum. I know that. Oh, I have OH. So now that I have OH, I can solve for H plus. One times 10 to the minus 14th divided by the 3.25 times 10 to the minus fourth. And I'm actually going to do that right here. I will then take the negative log of that value and the negative log of that value. Oh, not that value. Negative log of that value. So this right here is my POH. This is my pH. Woohoo! Awesome. Let's see if I missed anything. Where'd my questions go? Oh, hold on. We'll get back. Okay. pH, POH, OH minus, H plus. It's not a, well, it actually is a base. It is a base because it can pick up an H plus. It can also donate an lone pair from the oxygen, one of the oxygens. So it can pick up an H+, which makes it a Bronsted-Lowry base, and it also is a Lewis base. So that should be everything, and it's only partially dissolved. That was awesome. Okay, next one. I swear to God, we're almost done with this particular question. NaNO3. Okay, NaNO3 is neutral. It is a strong electrolyte because it's completely soluble. Dissociates completely. Ions. Na plus, NO3 minus. We are going to have some H plus and some OH minus. And H plus equals the OH minus, which equals 1 times 10 to the minus 7th. That means my pH equals my POH, which equals 7. Oh dear Lord, we found. And one more. Just one more. And then I can breathe, right? CH3, CH2. CH3, CH2 looks like a base to me. Let me go see if we can see where that is. CH3, CH2. Wrong table. CH3 and H2. I see none. Awesome. So that means it's not a strong base, it's not a weak base, in which case it's neutral. Looking at it, I have no reason to believe that this is going to dissolve. There are no ions present. So this is not going to dissolve. So it's not dissociated. It is not an acid, it is not a base. I am not going to get a concentration from CH3 or CH2. My H plus and OH minus are both 1 times 10 to the minus 7th, which gives me a pH and a POH of 7. So this also applies to this one. And that is the end of number 9. Now, I know that took forever, and I would never give you that many on a test. What my goal was here was to show you that, one, you should have been able to do it. Okay, all the information that you need to be able to do this is here. You have lists of strong acids and strong bases, so you should always know if it's a strong acid or a strong base. If it is, you know what that concentration is because it's completely dissociated. If you know that concentration, then you can use the fun box to find everybody. If it's a weak acid or a weak base, we can use the Ka or the Kb to solve for those concentrations and then use the fun box to find everything else. If it's a neutral compound, then we have to look at what kind of salt is it. So is it something that's going to react with the water like the BaCO3 did, or is it not something that's going to react with the water? So that's the kind of thing you should be able to do at this point. It's a long time, and like I said, I would never give you all of those on the test, but I wanted to make sure that you got practice with all of it. Okay? So I'm going to stop this one, stop sharing, stop the recording.